Thank you, Jerome. So this talk is going to be a little bit technical. So please, if there's anything that is not clear, please ask in the middle of the talk. So let's get started. This is a work that is involved many people. Of course, Stéphanie Duval and Jérôme Pelletier, and some students like Luca Ticini, Laura Rachman, and me myself, I was involved in the last part of the project, but the acquisition were done by Luca Ticini and Laura Rachman. So when I try to make this presentation, I think that it could be nice to have a description of art, what is art, but I guess I'm not the one the indicator to make this definition. So this is a question I will ask you later, because what is art? That is a question that scientists we depend on artists to define this. But there is a new field in the neuroscience that born from this interaction between art and neuroscience, and which is called neuroaesthetic, and is defined like the study of how and why humans respond to art. And this is a very new field, and it's about to respond to questions like how art creates aesthetic pleasure, or what is the nature of aesthetic experience. And how we do this? Well, basically, we put a subject in an fMRI scanner, or we measure some brain activity while this person is looking at a painting or listening to some music. So basically, it's that. It's a very reductionist way. We agree on that. But I think that we have maybe some important things that we can contribute to the understanding of art, perception of art mostly. So basically, what we found in this kind of studies is activation in brain areas like here in the occipital cortex, which are related to the perception of the visual stimuli, right? Because it's a painting, so it's a visual stimuli. We have activation of occipital areas, or temporal areas if it's a sound, right? But when we observe a painting, we only have this perceptual processing of the visual stimuli, right? We have a painting that evoke in us emotions. At least some people, this arousal kind of emotion or pleasure, or maybe trying to understand this painting, we try to make sense, and this evoke in us emotions. And emotions are widely studied, and there is a network of regions that is activated by emotion. So this is just basically to show you that there is some key nodes in the brain that are activated by emotion, and especially the orbitofrontal cortex, which is here. And if we look at neuroaesthetic studies, which is this slide is about a summary of neuroimaging studies on neuroaesthetic, we found also the same regions like orbitofrontal cortex, amygdala, and occipital cortex that are also activated by emotions. So in understanding the contribution of emotion to the perception of art, we can found some similarities, which is normal, because painting evoke in us some emotion, right? And as I said before, the orbitofrontal cortex is widely involved in this activation of emotion when you have to judge if this painting is you like this painting or you don't like this painting. You have activation of these areas. But these areas is also activated by other kind of pleasure. So it is not specific to the visual stimuli. It's a more general system that is involved in the appreciation of the level of pleasure you have from something. But there is also other brain areas that are activated when you judge a painting, for instance, in this study, that show that there is activity in other brain areas like the prefrontal cortex, motor areas, and areas of the attentional system. So this is interesting because there's some theories that try to understand, besides emotion, what could other neural systems could be involved in this appreciation of the art. And there's studies that have shown that the involvement of the motor system, which is the one related to the action, right? And that is activated when you observe passively a painting or when you have to explicit rate the pleasure you have of seeing a painting. And this is related to the nature of the aesthetic experience. If we wonder if this nature is merely perceptual, if it's all related to emotional brain system, of this experience may encompass other brain system. So there is this hypothesis that our work could elicit some activation of the motor system that could elicit a change in the aesthetic appreciation of the artwork. And there's many studies, and we were particularly interested in the study of leather that suggests that perceiving painting style elicits covert simulation of concordant hand movement in the viewer. And this stimuli-triggered simulation can be enhanced by interfering by simultaneously performing hand movements that either resemble or do not resemble, respectively, the movement adapted made while creating the painting, and making such movement should increase or decrease aesthetic appreciation. And that is, as later shown in this study, where congruent movement related to a painting style elicit enhanced appreciation to a painting in relation to a painting that is not congruent with this movement. So we aim in this study to understand the involvement of visuomotor processing and aesthetic experience. And we performed two studies, a behavioral experiment and a brain imaging experiment, and which is based on this notion that motor simulation could be involved in the aesthetic appreciation.
So to try to answer this question, what we did was to record subjects' preference for paintings. So I'm going to use the microphone. I can't do more, sorry, I have a throat ache. This is good? Yeah, okay. So to try to test this question, this hypothesis, we designed an experiment where we recorded subjects' preferences for pointillist paintings. And these paintings were presented under 3 conditions. Those conditions were either compatible or not compatible with the action required to produce them. So those were pointillist paintings, so an action congruent, compatible with the action required to produce pointillist paintings is dots. And its incompatible action, for example, can be producing strokes. So how did we do that? First, we used 3 hand images. One was displaying a hand holding a paintbrush using a precision grip. So the precision grip is a grip that is supposed to prompt the production of dots. It's a hand executing a stippling movement. And second, we used the image of a hand holding a paintbrush with a power grip that is supposed to prompt strokes, the production of stroking movement. And third, as a control condition, we used the image of a still hand that prompts no action. So on the first in the first phase of the experiment, before the experimental session per se, we had the subjects doing an associative motor learning. The idea here was to reinforce, to create an association between the participants' own movement and the pointillist style or the stroke style painting. So to do so, we had the subjects performing the desired action when they were viewing the different images. So when the subject viewed the precision grip image, they would execute stippling movements, and so they would produce dots on canvas. When subject viewed for a few seconds, this was controlled, right? When subjects viewed the precision grip, the power grip, they had to produce strokes on the canvas. And when the subjects viewed the still hand, they would move their hand palm down on the table. So this was to first create the association, okay, between my movement and the painting style, pointillist style, stroke style, and this was before the experimental session, and subjects did this learning in between scanning session or behavioral experimental session to reinforce the learning. So then came the experimental test, during which subjects would rate their preference for paintings, for pointillist style paintings. We validated 90 pointillist artworks, so those paintings were easily recognized as to be pointillist style paintings by some subjects that did a first round of experiment. So those are two examples among the set that we used. So we used the classical liking method. So subjects rated their preference on a 9-point liking scale. And each target painting was preceded by one of the 3 images that was used during the associative learning phase. And the idea here was to create the 3 conditions of compatibility between the painting and the action produced in the painting. So when the painting was preceded by the precision grip image, the condition was compatible, and it was hypothesized to facilitate action simulation. The hypothesis was that, well, the idea here is that precision grip prompts dot action, and this was reinforced, this was associated during the learning phase. And so this creates a compatible condition between the action here and between the action, the style, the action style. And when the painting was preceded by a power grip, force grip image, the condition was incompatible because this prompted stroke style painting. So it was incongruent with the points, the dots from the pointillist paintings. And the still hand was used as a control or baseline condition, priming no action, but still it was a priming condition. So then subjects would see each painting preceded by the 3 different primes, and we calculated the liking for each condition separately. Okay, so we measured, actually we did the average of liking responses for each painting separately for the compatible condition, incompatible condition, and the control condition. And the results showed that the liking responses were statistically higher in the compatible condition than the incompatible condition. So this effect is very small. As you can see, the mean is, the difference is only a few points, but still it was it was statistically significant. So this result was kind of a first proof that preference can be modulated by action priming, and when the action is congruent with the style required to reproduce these paintings. So when the painting was preceded by an action that was congruent with the pointillist style, people liked those paintings better than when it was preceded with an image that prompted an incongruent action. So next question was first to try to replicate those results and then to look for the neural correlates of this effect. And José Luis is going to present the MEG study that we did.
So yes, well, the next question was what are the neural correlates of this effect? So we tried to duplicate this protocol in an MEG experiment. MEG, why MEG? So we have two kinds of brain imaging methods. There are the metabolic ones and the electrophysiological. Metabolic like fMRI, that you maybe have you heard, and the advantage of these EEG and MEG methods is that we are able to track the neural activity on time. So we can look at the brain activity, how it's modulated in time. This is very important to make models about how the brain works. So basically what we measure is the electrical activity that is produced in cortical neurons in the brain. And this produces a current that we measure with special sensors that are sensitive to these signals. And we have for every sensor here the activity of a group of neurons. And basically what we do after is average many trials to understand how the activity is modulated on time. And we say that the early modulation of activity between 100 and 200 are early activation of the brain, and then there is later activation that are related to more sophisticated process. And we do that in a special chamber because the magnetic activity of the brain is very low. It's many times lower than the magnetic field of the Earth. So we have to use a special chamber for that. So we basically replicate the same protocol, and we have a technical problem here because we didn't replicate the behavioral results. So people don't like differentially if there is a prime that is congruent or incongruent with the style of the painting. But anyway, we wanted to understand what is the activity elicited by this visuomotor priming, because they can be give us some answers, some hints about what is the modulation of the brain activity in response to the art. So if you remember, this is the protocol, and in the painting part, we analyzed the brain activity that is elicited between the painting displayed and during 1,000 milliseconds, and before that the participants respond to the question, how much do you like this painting? So this is the activity of the brain for many sensors in the brain, and you can see here, but around 100 milliseconds, there is a peak of activity that is related to the visual percept of the painting. And then you have another kind of activity that is most sustaining in time. So to understand, to investigate this activity, we make a kind of average of this brain activity to note what are the peak of activity, because we are interested in to know where are the big changes in the brain activity. And if we compare first the prime and non-prime condition, we observe that there are a peak here in an early time window and a late time window where is this sustained activity, and we found difference at this level. So this is a little bit technical, but it's just to say that there are differences that appear in early time windows and late time windows. Okay, And this is related to perhaps to perceptual processing of the visual stimuli and late processing that is related to more sophisticated and cognitive process. And what we do usually in this kind of brain imaging.
The blue is what, prime, and the red is no prime?
Ah, yes. The red is prime, and the blue is no prime.
Okay.
Yes, yes. I don't know why it should be there, but yes. So yes, in this case, what we observe is the no prime condition elicit some differential activity in an early time window, and the prime condition elicit an inverse pattern here. There is more activity of prime in the late condition. So there is something happening there. And a way to visualize this activity is to plot the activity of the brain for every sensor here. This is a topographical map. And observe the change of the magnetic fields and what is the shape of this. And in this early time window here, this very first peak of here, you observe some difference in the magnetic field here between this condition and this. And you really can observe this difference here in an occipital region. You have to imagine this like looking at the head from above. And if you project this in a three-dimensional space, you could see something like this. Okay? So then what we observe for every instant, every peak here, there is change in the topography that tell us that there is some occipital change here, this difference here in the occipital areas, and here there is occipital activity that is spreading more frontal and then come back to the occipital. So this is what we normally observe to a visual stimuli activation in this part of the scalp. But to know what brain regions are actually involved in this activity, we have to perform another kind of analysis, which is called the source analysis, which is trying to look at the brain, because this is the scalp, but we need to move to the brain. And we do this kind of analysis, and we can look very specifically to which brain regions are involved. And if we look at in the very early time window, which is this peak we see before, what is the no prime condition, that is elicit more activity at the prime condition, we observe occipital regions that are activated, which is basically normal, by the visual stimulus that spread more to secondary areas. This is the V1 area, and then there is secondary areas because visual stimuli follows a hierarchical processing that goes from V1 and then temporal or parietal areas. And then there is a late time window where we see the parietal region activated and some temporal areas, which is the typical processing of the visual stimuli. Then in a late time window, we observe the opposite pattern. There is more activity elicited for the prime than the no prime condition, and this is come back to the occipital region, which is also interesting because it's like the activity in this late time window is coming back here. There is some kind of reprocessing of the visual information that in the first place goes from occipital to parietal or temporal areas, and then in a late time window come back to occipital areas. So for the no prime condition, we observe that some this maybe suggest there is some the prime condition could elicit some repression of activity that could be related to facilitator effect or maybe perceptual effect, but because this is an early time window. And in the late time window, we observe something that is a cognitive effect because it's late, but come back to occipital region. So tells us that there is some reprocessing of visual information. Now, what is important to us is to understand the difference between the congruent, incongruent, and the control condition, which is no action. And we also look at the same time windows to observe some differential change here. And even if there is no easy easy way to visualize here, we do observe some difference in the latent windows here. And what is interesting is that when we perform the source analysis, we observe some frontal areas that seems to be involved in this early time window that is different for the congruent and incongruent condition. We observe also this for the congruent versus no action, and in the congruent versus the incongruent condition. So all this is a little.
Sorry, I'm struggling with it.
Yes, I know.
So you've got the prime condition. There's a congruent and an incongruent prime.
Yes, for the prime we have three conditions. We have congruent, incongruent, and no action. Right.
So the images that we were seeing before, where it was prime versus no prime, the graph for prime was averaged across the different priming conditions.
Right. We take all the conditions where this congruent condition. You mean for the prime we average all the primes, the congruent, incongruent, and no action, and this confirms the prime condition. And the no prime is only when there is no any prime.
So the hand just there is a prime.
It's a prime, right?
So there are 3 primes.
Yes.
And the prime versus no prime, prime was averaged across the 3.
Yes, right. That's it. And so, yes, and then in a late time window, what we observe is again that there is an occipital activity that is widely activated between some conditions. So this is a little bit hard to understand, and we are still trying to make sense of this data. But what we basically know now is that there is some early activity that is related to frontal difference between the congruent and incongruent condition and the no action. And this maybe, we have to verify this of course, but maybe mean that there is some motor involvement, or well, not necessarily motor involvement, but at least frontal activation of these areas. And then in a latent window, we observe again there is a difference between this condition, and I didn't show here very well, but this could be related to some limbic activity that can be hippocampus or amygdala, but we have to confirm this, that may be related to emotional system. Okay, so basically what we found here is that this visuomotor priming paradigm is useful to understand the neural dynamics of aesthetic appreciation. We have to perform different kind of experiment, because unlike a previous study, we didn't modulate affective response here, so we have to find a way to correlate this affective response with the neural response. And for the brain imaging experiment, we observed that the prime versus no prime condition elicit a biphasic effect, suggesting an early suppressing effect of prime and gain mechanism from primes. Okay, and this early enhanced visual response to the no prime relative to the prime, our work converged with previous evidence that showed that there is an early innovation of target processing by primes. So in part, this is congruent with the previous studies. Now, for comparing the 3 conditions, we have to dig more in this result to understand to make sense of them. But basically, congruency of the prime with the painting style elicit different activities and occipital region, which is typical from perceptual processing, and parietal and frontal brain regions. So overall, this visuomotor priming paradigm promotes neural change during the visual processing of target, and this effect changes in the time. And although these neural changes were not reflected in differential behavioral response, the result showed that the visuomotor context impact the visual processing of artwork. So overall, this visual motor priming with our behavioral experiment and our image experiment allow us to test some hypotheses regarding the motor nature of its perception. And the second experiment maybe can give us maybe some hint about the mechanisms that impact the nervous processing of artwork. Thank you.